Let's talk about the discharging RC circuit. So an RC circuit has a resistor and a capacitor connected in series, and there's no power source connected with them. The capacitor is fully charged to begin with, and it's going to essentially act as the power source in that it's going to be driving the circuit. It's the thing that's going to be pushing the circuit instead of some kind of battery. So this is the discharging RC circuit. And in this case, I'm going to say that this side of the capacitor is positive and that side is negative. So what's going to happen here is I've got all these electrons right here that are grouped together. And of course, they're all the same polarity, so they repel each other. And once this circuit is completed, those electrons are going to push each other off. They're going to go this way all the way around through the resistor to get to the positive side of the capacitor. And initially, there's going to be a lot of repulsion. And because there's a lot of repulsion to begin with, that means the current is going to be high. The charges are going to be pushed off quite rapidly. And so in our graph here, I've got a plot here. I've got charge of the capacitor versus time. So we're starting with some initial some initial charge, and it's going to be easy to push those charges off. So we're going to have a steep slope because it's quickly going to leave the capacitor. But as they leave, that means less repulsion. There's less repulsion to drive that current, and so then the current is going to decrease. Fewer charges are going to be pushed off the plate every second. And so we get exponential decay. Now let's look at this using the loop rule. So for the loop rule, I'm going to go counterclockwise. So that means my current, in this case, I'll draw my current this way. So I've got, let's see, it's going to be, now I'm going around like this. So I'm going from negative to positive. So the capacitor is going to be positive, but the resistor, it's going to be minus VR equals 0. So now we can go ahead and put in our relationships. We say this is Q over C minus IR. This is going to be equal 0. So these are obviously going to equal each other. Q over C is going to equal IR at any moment in time. So if we want to look at the beginning, if we want to look at T equals 0, okay, then that means Q equals Q initial. And so I'm going to have Q initial over C, and that is going to equal I initial over R. And if we want to look at some later time, if we want to look at infinity, well, when we get there, Q is going to equal 0, and so all I'm going to get is 0 equals 0. So this implies here, in this case, this implies, saying Q equals 0, this implies that the current is 0 after an infinite amount of time has passed. So notice that our current starts out high because the charge is high, so the current starts out high, but then the charge goes to 0, so does the current. And we can also look over here at our graph. Remember that I is delta Q over delta T. Now technically, because I has to always be positive, it's actually the absolute value here. But it's essentially, it's the absolute value of the slope of this graph. And the slope is quite high. So I'm looking at this graph here. The slope is quite high, or I should say is quite steep. And then it becomes shallow. It flattens out. So that means the current is going to start out high. Current's going to start out high, some high initial, but it's going to decrease exponentially. If you go through with calculus, you can show that both of these are indeed exponential decay. The formulas are Q equals for the charge of the capacitor, e to the negative t over tau, and the same thing for the current. Exponential decay in both cases. And in the last case that I want to look at, when t equals tau, oh, and I should mention tau is equal to RC. If you're looking at the units, this is called the time constant, tau. It's measured in seconds, and that means an ohm times a farad is equal to a second. And again, this is just called the time constant. It's just the resistance times the capacitance. That's how you calculate it, and that's derived from calculus. So when t equals tau, these formulas tell me that, okay, Q sub C, the charge of the capacitor, is going to be Q initial times, that's going to be e to the negative 1, and that is approximately equal to 0.368. And if we're looking at the current, we're going to see the same thing, e to the negative 1, 0.368 times the initial current. And so now if we go to our graphs, if I locate 0.368 Q initial, so right there, okay, and I go across, and then when I hit the graph, then at my plotted points, I just come straight down. That has to be tau. And the same for the current. You locate 0.368 times the initial current. And that has to be tau. This is a way for us to get the time constant from the graph, just by reading the graph. The most precise way would be to go through calculations, of course, but you can use a graph and you can quickly narrow in on what the time constant has to be using this technique. And by understanding these relationships here, which come from our equations, but understanding how these come about and understanding that it's 0.368 times the initial value. So this was the discharging RC circuit. The last thing I need to mention about this is just has to do with these formulas here that we have. These formulas are derived assuming that the charge can be as big or as small as we want, but in fact, there is a smallest value. So it's not true that they can be any value we want. The current is carried by electrons, and electrons have a specific amount of charge on them. And so that means that this is not 100% exact. Right? But if you're talking about huge amounts of charge, which for our purposes in our everyday lives, yes, we are dealing with enough charge that that's the case. When you're talking about large amounts of charge, these formulas, this model is really good. It's a really excellent model. But I do want to point that out, that it's not 100% precise because, again, the electrons are the smallest amount. We can't get to any arbitrarily small amount of charge. The smallest amount is the charge on the electron itself. But that's everything I want to say about the discharging RC circuit. If you're interested in the charging RC circuit, you should watch the video on that.